The drill bit. That's all it does, all day long when it's on bottom. Think about this for a minute. Engineers design rigs. Welders put the thing together. Boats tow it out onto location. And everybody's job on board when they're on tower has something to do with making that bit turn. Sure, the equipment's doing a lot of the work, but when you really think about it, it's all the time and effort put in by people like yourself that make that bit turn and turn and turn and turn and turn. This is the first of a series of programs that will introduce you to the world of drilling bits and drilling practices. It's targeted for you, the drilling hand, so that it may expose you to some of the things you don't already know. In programs to come, we'll be exploring everything from what causes bit failures to some of the practices you should be aware of as you go about making hole. In this program, we'll be taking a look at bit designs that were used long ago, as well as the types of designs that are being used today. Specifically, we'll be concentrating on the fishtail, rock, and diamond bits. We'll also take a look at the polycrystalline diamond compact, or PDC bits, which have gained acceptance in the marketplace. The drill bit. Not a very complex piece of equipment, but probably the most important one on the rig. Without it, you don't make hole. And when you don't make hole, you don't satisfy the customer. This is what a drill bit looks like today. They come in various sizes and are manufactured by many companies to fit your drilling needs. They're made to drill through three basic types of formations: soft, medium, and hard, as well as a combination of the types. A long time ago, the first rotary drag bit, the fishtail, came into being. It was a simple bit, only had two blades and an eye for the drilling mud to go through. The blades were made as one with the bit body and would rotate as a unit with the drill stem. This type of bit, and its current counterparts, are still being used, but they're really limited to drilling through soft and gummy type formations. Then the roller cone, or rock bit as you may know it, came into the picture. This type of bit allows us to overcome the higher compressive strength and abrasive rocks. With the innovation of the rock bit, the drilling industry changed dramatically. Let's go ahead and take an in-depth look at this bit, since it's probably the one you're most accustomed to seeing. This is the bit shank. It contains information such as what type of bit it is, its size, the assembly number, and so on. Here's the nozzle boss, or socket. Inside it is a jet that allows the drilling fluid to be directed downhole. This is a sealed journal bearing. Each cone is attached to one of these journals that provides the rotating action for the teeth on bottom. Above the journal is a passageway used to connect the journal to a grease reservoir. Here is the pressure compensator system. It balances the pressure inside the bit with the external hydrostatic pressure to minimize any differential pressure across the seal. Here's one of the cones of a bit. On a rock bit, you'll have cones of teeth that do all the work. Depending on the type of bit you'll be drilling with, the teeth will be made of either steel or tungsten carbide. This is the bit leg, or lug. On rock bits, you'll have three of them welded together to form the actual bit itself. The lower part of the bit leg is the shirt tail. It's the part of the bit that the cone is attached to. In most cases, you'll see that hard facing is applied to the shirt tail to minimize wear when it comes in contact with the wall of the hole. Rock bits are classified in two categories: steel tooth and tungsten carbide insert bits. Regardless of the category they fit in, each bit consists of major components such as the cutters, bearings, and fluid courses. We'll take a look at the cutting structures first. Steel or milled teeth are part of the cone structure. When we say they're part of the structure, we mean that they're milled out of a single piece of steel. Insert bits, on the other hand, have their teeth inserted or pressed into the cone. They're made of tungsten carbide, providing a longer lifetime for the teeth. When you look at a steel tooth bit, the teeth are usually long and pointed. If this type of bit were to be applied to a soft formation, penetration rate would really be fast. Of course, appropriate weight on bit and rotary speed are also necessary, but you can see that the teeth, because of the way they're shaped, could really make some hole. When you consider a type of bit that's going to give you good penetration, remember that there are other factors such as cone offset and intermesh of the teeth that will improve penetration rates. Cone offset is the difference between the center line of the cones and the center line of the bit. Let's take a look at this diagram that shows offsetting of the cones. Here is where you see the offset alignment. As the cones rotate, they're forced to rotate about the bit center line. As they do this, they tend to slip, which provides the tearing and gouging action that you want in soft formation type bits. Intermeshing of the teeth provides a self-cleaning effect, better utilization of space, and encourages twisting and tearing action as well. Picture that the teeth of one cone intermesh with the groove of the teeth of the other cones. Let's look at this example. You've got a left hand and a right hand. As the right hand moves closer to the left, the fingers of the right hand intermesh with the grooves of the left hand. The same goes for the teeth on a drill bit. This intermesh provides a cleaning effect, because if any junk gets trapped in a groove, the teeth push it aside, providing a clean area. When you drill through medium and hard formations, you'll need to use a bit with different characteristics. For instance, you'll find that the number of teeth will increase with the harder formation designs. They'll be spaced closer to each other, there will be little, if any, offset, and the shape of the teeth will also change. Now let's take a look at the insert type bits, since they've really become predominant in the oil field, especially for the harder formations. The principal difference between insert and steel tooth bits is that the inserts are more wear resistant and also help to reduce trip time, because the same bit could be run through different types of formations. If you're drilling through soft formations, the bit will have a few widely spaced inserts, and they'll extend as far as possible from the cone shell to allow maximum penetration into the formation. The cones will also have a good amount of offset to help provide the kind of cutting action you want on bottom. There'll also be a great deal of teeth intermesh. As you drill through, say, a medium type formation, the inserts still may be chisel-shaped, but they'll appear to be somewhat blunt. They're going to be more closely spaced and still may have some offset alignment. Hard formation type inserts become even blunter, and more inserts will be added so they can provide maximum coverage of the whole bottom. Usually there won't be any offset, making the bit action on bottom true rolling. This true rolling action of the cones complements the additional weight on bit that's needed for penetration, because the inserts stay on top of the rock as opposed to digging into it. To make hole in this type of formation, you have to crush, chip, and fracture it. You can see that the soft formation bits respond to a moderate amount of weight and more rotary speed. As you drill through tougher formations, it's just the opposite. You add more weight and have less rotary speed. Now that you're familiar with the kinds of bits that are used in the different formations, let's take an even closer look at the drill bit and see how other parts function to keep it turning on bottom. The development of the sealed journal bearing has proven to be a key factor in bit life. In the past, a bit would only last as long as the bearings would hold up. The biggest problem with this was the intrusion of abrasive drilling fluid in the bearings. This isn't the case with the sealed journal bearing assembly. Let's take a look and see why. The journal takes on the applied weight as the bit's working on bottom. The seal is necessary to keep fluid from entering the bearing. It keeps the lubricant in and the mud out. The upper portion of the bit is where the lubricant reservoir and compensating system are located. The reservoir acts as a storage place for the lubricant, and the compensating system minimizes differential pressures across the seal. The other major components of a drill bit are the fluid courses. They're designed to direct the drilling fluid onto the teeth and formation. Conventional fluid courses, or regular circulation bits, were designed to direct the fluid onto the teeth and then to provide enough angular velocity to bring the cuttings up the hole. Today, jet-type fluid courses direct high-velocity fluid onto the teeth and formation. There is also enough velocity to lift the cuttings up the annulus as well as create enough turbulence around the bit to clean the teeth properly. Hydraulics are very important in rock bit design because the teeth and formation have to be kept clean in order to make good penetration rates. We've spent a good deal of time on rock bits because it's probably the one that most of you have worked with. The rock bit has really become a standard in the business, and therefore we felt that more time should be spent on it. Let's now take a look and see how diamond and PDC bits differ from rock bits. When you compare a diamond bit to a rock bit, it differs in many ways, from the way it fractures the formation to how much it costs. Diamonds can be classified in two categories, natural and synthetic. Any way you look at it, they're very expensive. For instance, this Carbonado diamond was weighed at 112 carats and has a dollar figure of $39 a carat. That amounts to $4,368. The reason diamonds are used in drilling is that they're hard and are tough to break. When we talk about a diamond's action on bottom, it varies quite differently from a rock bit. Basically, a diamond bit breaks the formation in three ways. It can compress, shear, or act like sandpaper and wear it away. Let's look at the parts that make up a diamond bit. This is the connection that attaches the bit onto the drill string. The cylinder-shaped part that contains the breaker slot is called the shank. It provides stabilization for the bit. This area here is called the gauge. As the bit drills downhole, the gauge provides the diameter of the hole. As part of the gauge, you can see the junk slots. They serve as passageways for fluid, which flushes the cuttings away from the bit. This entire area here is what the diamonds themselves are situated on. It's called the crown of the bit. Now let's look at a face view of the crown area. The center of the bit is called the crow's foot. Hydraulic fluid is distributed down the crow's foot to the primary fluid courses, which are actually a part of the bit gauge. They extend wider than the secondary fluid courses, which are part of the junk slots. Now let's look at some of the crown profiles and see how certain designs can affect bottom hole penetration. We've got three basic types of profiles used in diamond bits: the round crown, tapered, and extended tapered crowns. The shoulder area of the bit is situated between the gauge and crown. When we get into the distinguishing characteristics of the profiles, notice how the shoulder areas of each change. The part of the bit that actually touches the formation is called the nose area. The indented area here is called the cone. It provides more surface area for diamonds and also provides stabilization to help keep the bit from moving sideways. In the round crown configuration, the shoulder area is large, which allows the crown of the diamonds to cover more formation. Look at the shoulder of the tapered and extended taper profiles. Notice how they get shorter? This provides a smaller point to attack the formation. These two types of profiles are not as strong as a round crown, but they provide a faster drilling penetration. One more subject that needs to be covered is the fluid courses. There are two basic types, the radial flow and cross-pad flow. In the radial flow, the waterways start out narrow at the center of the bit and then widen as they get closer to the outside diameter of the bit. The narrowness of the patterns allows the drilling fluid to remove the cuttings, but as the pathway gets bigger, it becomes difficult to maintain enough velocity at a high enough rate to obtain good cleaning action. The other type of fluid passageway is the cross-pad flow. Drilling fluid moves across to the primary fluid courses at a high pressure and then crosses to the low-pressure secondary fluid courses. Notice that the passageways have a constant width as they extend toward the outside diameter of the bit. The way we use diamond bits today is to simply compress and crush the formation. Sufficient weight applied on the bit causes the formation to fracture. In the shearing mode, the diamonds are used to dig through the formation, allowing the cuttings to be scooped up in front of the bit. Diamonds can also drill through the formation in an abrasive mode. Usually this method is used when the formation is so hard that the only way the bit can break the formation is if it were to act like sandpaper, eventually wearing it away. You'll find that a diamond bit used for soft to medium formations will usually have fairly large diamonds and be widely spaced. The larger the cutting surfaces are, the more hole you're going to make. Diamonds that fall under this category are commonly in the 2 to 5 stones per carat range. Diamonds that will be used for harder type formations will increase in number, become smaller, and closely spaced. You may even see an extra row or two added to help the cutting action on bottom. When you get to the hard formation diamond bits, the number of diamonds will increase, as will the number of rows. The diamonds will become smaller, usually in the 8 to 12 stones per carat range, and will be densely spaced to help provide for longer life. Now let's take a look at the PDC bit, which is used to drill through soft and medium type formations. It's made of a polycrystalline diamond compact bonded to a tungsten carbide base. This combination provides hardness, wear, and impact resistance while drilling. Here you can see at least two of the shapes the cutters are manufactured in, the stud type and cylindrical shape. Other advantages of the PDC bit are that there are no moving parts, and the bit is self-sharpening. PDCs can be manufactured either in a steel body or tungsten carbide matrix design. They're made to shear the formation away as opposed to gouging or crushing like a rock bit. This PDC bit has just been put through a formation test at Reed's Pressurized Drilling Lab. Notice the cuttings that have been collected. You can actually see where the cutters have sheared away the rock as it was turning on bottom. When drilling through soft formation, the cutters are usually fully exposed, allowing a very aggressive and rapid penetration rate. Harder formations require less cutter exposure, but more cutters on the bit body. The fluid passageways in PDCs are the nozzle or port type. You'll recall that there was a pressure drop of fluid in the diamond bit as it made its way across to the outside diameter. Well, in PDCs, the only pressure drop would be at the interior of the bit and across the nozzles, but not across the face of the bit. By now you can see that there are a variety of bits on the market today. We've mentioned only 4 of the most common types: the fishtail, rock bit, diamond, and PDC. The important thing we want to stress in this program is that there are various types of bits for the various types of formations you'll be drilling through, and that the cutting action of each type of bit is different. Coming up in this series, we'll be discussing bit failures, proper drilling practices, bit hydraulics, and bit selection. Good luck and safe drilling.